Hello, it's Keith here, and this is lesson 2 of the 2021 series of Z80 programming tutorials. This is the refresh series for 2021. Today we're going to be looking at the addressing modes of the Z80. What are addressing modes? Well, this refers to the way that the commands will either get the source for the data or the destination of the action of the command itself. Now, the Z80 has a wide variety of these, and in today's lesson we're going to go through each of them with a set of examples, and some of these you'll have seen before and some of these are a little bit complex and maybe you won't understand at this point, but the intention of today's episode is that we're going to go through each one in turn, and you will have seen them all by the end of this lesson. So hopefully this will be a good one for you to maybe come back to later to double check things when you've got questions or you need to see examples of some of the commands, and also so that you can, going through into lesson 3, know that you've seen all of the possible addressing mode methods and that there's nothing really left that's necessarily going to surprise you. So as always, we've got an example we're going to run today. We're going to be running it on the MSX2 today. The example should run on most of the other systems if you would prefer to do a different one. Some of them directly addressing memory may not work the same, but as I say, it should generally work on all of them, but we'll be trying on the MSX2 just to make the point that we are a multi-platform series. Of course, the build scripts and the source code are available from my website as always, and also you can go to the website and there's the documentation, which you can see on the screen at the moment, which will cover all of the topics in this video as well. So if you need to see it at a slower pace or you prefer to read text rather than watch videos, that's there for you. Anyway, let's go over and let's see today's example. Okay, so here is the example, and we've got a series of jumps at the start here, and we just need to enable one of these to run the appropriate test. And the first one we're going to do is immediate addressing. Now, immediate addressing isn't going to be too surprising for us because we've actually seen it before. So immediate addressing is exactly what we saw at the very start of the first lesson. This is where we load a register or a pair of registers with an immediate value that is basically a number that is fixed, that is specified in the line of code itself. So here we're loading the accumulator with -10, and here we're loading HL with the decimal number 16383. Here we're loading BC with the hexadecimal number, that AND symbol denotes hexadecimal ABCD, and here we're loading D with the binary number 11110000, which is going to be F0 in hexadecimal. And here we're loading E with hexadecimal 69. And well, if we go over to our running example here, you can see that the accumulator has been loaded with F6. Now we loaded the accumulator with -10. So if we just get our calculator up here and we just put in here -10, you can see that -10 is indeed F6. So we have done that correctly. We always need to check these things. And then what we did next, we've reloaded HL with 16383. Well, HL has been loaded with 3FFF here. And if we just get our calculator up again here and we type in 16383, well, that is, of course, 3FFF. I mean, proving the obvious here, but we just always need to make sure that what's happening is really correct. So that has loaded in correctly. And then we loaded in D with quadruple 1, quadruple 0. Now each 4 bits is 1 nibble, which is 1 digit, if you will, in a hexadecimal. So this will be F0. I don't need the calculator to confirm that, so you can see that there. We loaded E with hexadecimal 69. Well, of course, these are being shown in hexadecimal, so you can see the 69 there. And that is the end of this series of tests. So you can see there that we've successfully loaded a series of immediate values into our registers there. As I say, immediate is sort of the most basic method of addressing, I'd say. The values are fixed. So this is how we load our starting values for registers and things like that. Now, the next one we're going to be looking at is known as register addressing. Now, this is also something we've already seen. Register addressing is simply where the source or destination is a register, which is going to be most cases. And here we're going to see cases where both the source and the destination are registers. So let's fire this up. Now, of course, we did see this last time as well. It's really impossible to write anything without doing some register addressing. So we've loaded some test values with immediate addressing here. So we've loaded those values in. And then we're going to do some commands with register addressing. Now we can load most of our registers as a source or a destination with the load command. Of course, as always, the source is on the right and the destination is on the left. So H is being loaded into D in the first line there, and L is being loaded into E in the second line there. Now with some of the very unusual registers like I and R and IYL and things which are more limited, you can't transfer these necessarily to any register. If you need to be sure, please check out the cheat sheet you can download for free on my website. That will help you out, just showing all the commands that are possible, and thus anything that's not on there is not possible. Now, register addressing in this form, where we're just loading from one register to another, can only work on 8-bit registers. We can't load a 16-bit register. So if we want to set DE to the value HL, we have to do that in 2 separate commands in the way you see here. Now, HL was loaded with 0666 here, and you can see here DE went from all zeros to 0666 here, so that has been successfully transferred by this command here. Now there might be cases where you want to swap the top and bottom parts of a register pair. Now you can do this, but you can't do it in 2 commands, because if you did, then you would overwrite part of the pair in the first command. So what you can do is you can use the accumulator as a temporary part. So you can see here the first line here is loading the value from L into the accumulator. Then L is being set to the top part, the H part, and then the H part is being set to the accumulator. So the 2 H and L parts have been swapped here via the accumulator. Of course, the accumulator has been changed there, so if you needed that accumulator, that might not be the option for you. And you can see that has happened here. We've gone from 0666 to 6606. So that has indeed occurred there. So again, a very simple addressing mode, not too exciting. The next one is referred to in the documentation as extended addressing. Now this is actually where we use the memory as a source or a destination for our commands. So in this case, we're going to be reading and writing from memory addresses C000 onwards. So this one might not work on some of the systems if that part of memory is ROM. It works on the Master System Game Gear, it should work on the Spectrum, and the Amstrad CPC should be okay, although that's actually screen memory on that system. But that's what we're going to be doing here. So let's fire up this example. Now, as I said before, the way that we specify that a value isn't an immediate, but in fact an address, is we put the value in brackets here. So if you see the case here, this is effectively saying load BC with the value at address C000. If we took the brackets out, if I just remove this and this, that would now be saying load BC with the immediate value C000. So the brackets here mean that the C000 is an address and that the value at that address should be loaded into BC. And in these cases, the value A should be loaded into the address C000. Again, source on the right, destination on the left, as always with Z80. Let's see what's happened. So we're showing part of our memory to the screen with this monitor memdump routine I've written. So this is going to show part of the memory. You can see the starting state of C000 here before we did any of our work. And then we've transferred the 69 value in hex to the accumulator, and then we've loaded the accumulator to memory address C000, which is at the start of this range, and you can see that that 69 has been loaded into C000. Right, that's the first command, and then what we've done is we've loaded the accumulator with 77, and then we've loaded the accumulator to C001, and you can see that just here. And then finally what we've done is we've loaded from C000 into BC. Now, if you look at BC, BC now equals 7769. Now, at the address C000 after our commands was 6977, so it may look like that has been swapped over. Now, I did explain this last time, but basically the Z80 and most of the modern processors are what's known as little endian, and that means that when we store a value from a register into memory, the lowest byte in the pair, or the quadruple in a 32-bit system, the lowest byte is stored first, and then each successive byte is higher in its importance. So in the case of a 16-bit pair, the low byte is the 69, that's stored first. The high byte, the 77, is stored second. So that's why we see that reversed. But of course, if you load back, it will be loaded back in the same format as it was saved, because it's just a function of the processor, the order it chooses to save its values. But we do need to know that in case we're going direct to the memory. So there we go. So that's some examples of extended addressing. Now it's important to understand again that we can't mix and match these in all cases. So if I decided I wanted to load the memory address C000 with the immediate value 69, well, I can't just take that off there and paste it in here. This is not a valid command. So if I try and run this now, well, it doesn't run, and I will actually get an error message. And you can see here it says illegal operand types. So again, if you need to check these things, please go ahead and download the cheat sheet. And also, as I've said before, this is why it's important to try and download the examples and have a go with this kind of thing yourself, because you know, if you're only seeing examples in books and things, personally anyway, I couldn't get fully to grips with the limitations and the capabilities of the commands just from seeing other examples. You need to actually start thinking it through and trying them out yourself and realizing the ones that do and don't work. Okay, we're going to take a bit of a side jump now to a very different type of command. This is known as relative addressing. Now, relative addressing is where the command relates to the current running line of code within the compiled program. Now, this is referred to by the program counter, which is an internal register within the Z80, which points to the byte of memory that is the current running command. It's not something we really going to discuss too much at this stage, but it is an important thing. Now, relative addressing is where the compiled code, rather than storing an absolute address like our C000, for example, it stores a relative offset from the current running line of code. Now, on the Z80, there is actually only really one command that uses this, and this is the jump relative command. So you can see here, for example, at the start of our program, we've shown a character to the screen with this print char routine, and then we've jumped relatively to skip 1. Now, skip 1 is just down here, so that's going to just jump down to this command here. Now, the fact that it's a relative jump has two differences to a normal jump, which would be specified by JP. Now, in this case, both would work exactly the same from the point of view of the function of our program, but there's an important difference. A JP command will specify the address skip1 in the compiled program as a pair of bytes, so 16 bits. The jump relative will just be 8 bits, and it will be a signed number from -128 to +127, which is the number of bytes to move the program counter along to skip to the specified label. The amount to jump will be calculated by the assembler. So that's the first difference, that it actually saves a single byte of memory, which is actually important when you're doing retro programming and you've only got 64K of memory. So if possible, you always want to use jump relative. The problem is, though, of course, the limited range is -128 to +127. So as your code gets bigger, some jumps will be impossible using jump relative. There is also another important difference, which is going to be probably too complex for you to worry about at this stage, but I will just mention it. Relative jumps allow for relocatable code. Now, when we compile our program, commands like JP that specify a label, well, if we compile to memory address, for example, 1000, that skip1 will be changed to a value like 1050, for example. But then if we moved that program in memory from memory address 1000 to memory address 2000, the jump would still point to 1050 and the program would no longer work if we ran it at that new address. But the relative jump, because it's an offset from the current line of running code, well, the offset will still point to the equivalent position in our program. So jump relatives are handy for relocatable code. Now, as I say, totally understand that's going to be way outside of what you need to worry about at this stage, but I do like to try and explain all of the things that I think it's important to know about, and if you don't understand them, just ignore them and you will come to understand them later on. Now, what's this program going to do? Well, this subroutine starts at this relative command here, and then we're going to show an aid to the screen. Now, we're then going to jump relatively to the skip1 label, and that is going to skip over this one print char command here, so that will never happen, and we'll jump here. We're then going to jump to skip2. Skip2 is actually before, and this is to show that we can go backwards in memory here. So you can see here we're then going to print a B, and then we're going to jump relative to skip3. Well, here's skip3, and you can see we're going to show a C to the screen. So really we're just going to see if this program actually works and shows the values we would expect. So here is the program running, and you can see we've shown A, B, C to the screen. And so the skip here has jumped over this, and the skip here has jumped back up to here. So that's worked just fine. Now, just to make the example of the limitations of the jump relative, I've defined a section of 128 empty bytes here. Now, the jump relative command can only do -127 to +128. So when I try to jump to this long jump, the jump relative command will fail. And you can see here I've got the error message jump long, out of range for 8-bit expression. So we cannot do that relative jump because of that extra section of code. Now in this case it's just an empty block of zeros, but in your real program that would probably be important code. But in this case you would need to change from a jump relative to a JP, a normal jump that specifies the full 16-bit address, and now our program will compile just fine and run. Now of course in this case the jump has actually just ended the program, but we weren't even able to compile before with the jump relative. So that's the difference between JP and JR, and as I say, that's really the only relative addressing mode compared to the program counter. Okay, so what we're going to look at next is one of I think the most important for writing proper programs that are actually going to do things, little games and things. This is known as register indirect addressing. Now we've seen how we can load from an immediate value, and we've seen how we can write to a fixed memory location. But we're not really going to want to continuously write to fixed memory locations. We're going to want to write to various and changing memory locations. And register indirect addressing does this for us. Let's fire it up. So what is this? Well, in this case, we are going to specify the source as a register, the L register on the right as usual. And the destination, you can see we've got HL specified. But HL is in brackets this time. So it doesn't mean store L into HL. It means store HL into the address in HL. So HL contains an address. In this case, the address is test RAM, which is some memory that I've allocated for us to use here. And you can see that that is 8340 here, and we've actually dumped that address to the screen so we can see what's going on there. And so what we're going to do is we've created a test value. We've loaded the immediate value 0666 into DE, and we're going to use the memory address in HL as the destination for some commands. So our first command here says load L into the address in HL. That's what the brackets mean there. And then we've incremented HL, moving to the next memory block. And then we've said load the value in H into the address in HL. And then we've inked HL again. And what this has done is it's loaded the value that is in HL 8340 into the memory address here, and you can see we've reversed them. We loaded L first and H second because this is a little endian processor. So if we want to read back from the address in this kind of format where the processor is loading both bytes in one go, then we need to make sure we store them in that format here. Now we can't load more than one register, 8-bit register at a time here. So to store the 16-bit HL value, we need to do that in 2 commands here, and we need to do an ink in between them, but that will store that 16-bit value just fine. Now after H and L, we've then stored back D and E here, and you can see here that that 0666 has been stored here as 6606. And so if we just go to our blackboard here, just to make it clear, so basically when we have a command LD HL D, we've got our register D, which is the source, and we've got our address register HL, which maybe contains D000, just for argument's sake. Now our D is the source, but our HL isn't used directly as the destination because of these brackets. That is used as the address, and this becomes the address. And so if we've got our memory D000, then the destination for D will become this address here. So these brackets here specify that HL is indirectly used to calculate the destination memory address. So D is stored to the address in HL in this case. Now here we've seen this done with HL being the destination for the saving of some registers here, but we can also use it as the source, and that's what we've done here. We've specified HL as being the test RAM plus 1. So we've started from an extra byte along here. And then what we've done is we've loaded A from the address in HL, C from the address in HL, and B from the address in HL. So let's see what that has done. Well, we started with the HL being offset by 1 this time. So we've effectively loaded in A with the value 83, that's this value here, and then we've loaded BC with the value 0666, and that's because again we stored in 6606, but because we loaded them back in little endian format, that has been restored to the 0666 value that we expected. Now the Z80 is actually quite powerful, and the HL register pair has a lot of special functionality. Now basically this can be used with a wide variety of other commands, and this, as I say, you really need to get that cheat sheet to fully understand the capabilities. But rather than specifying an immediate value for commands like add and subtract, and even other commands which we've not gone into like XOR, which we'll cover later, we can actually use the indirect address in HL as the source for those commands. So for example here, this add command will add to the accumulator, but rather than adding an immediate value, it's saying add the value at the address in HL to the accumulator. Now in this case here, we've loaded the accumulator with F0, and you can see that here, and HL was still pointing to this 06 just here. So when we've done this add command here, then we've effectively added the 6 to the F0, and we've ended up with F6. And we've done this all as a single command, so there's no need to load from the memory address in HL to another register and then add that register to the accumulator. We can do that all in one go. Now this register indirect addressing can also be used with the jump command. Now in this case we've loaded the address of the label jump test into HL, and you can see that just here, and it's going to show a right arrow here. And what we've done here is jump HL in brackets, and this means jump to the address in HL. Now that's going to skip over this exclamation mark to here, and then we're going to show that right arrow here, and you can see that's what we've done just there. Again, this is an advanced thing that you're going to need this kind of method very early on. You're going to benefit from, but you don't really need this kind of thing with the other commands. And this sort of jump to address in HL, you may never need it. It depends on what level you get to and things. But as I say, I want to explain all of the potential of these commands, so you've got a good foundation as you progress into your programming. So you can come back to this when you have questions, or you've started to think you might want to use some of these more advanced modes and you need to know about them. And we're going to go into one of the more powerful ones now, which is indexed. Now, quite similar to the 6502, the Z80 has a pair of index registers. They're referred to as IX and IY on the Z80, and they're 16 bits. Now, what are these? Well, these, like any other register, we can load these with values here. We've loaded them with two immediate memory address values here. We've loaded the test RAM address into IX and the test RAM plus 8 into IY here. So these registers now contain these values. We've then loaded some test values into A and B, C. But of course, this isn't the new method of addressing we're going to look at now. The indexed addressing, and this can only be done with IX and IY, is where we can specify the source or destination for some of our commands as being an address in a register, IX or IY, plus a fixed offset specified like an immediate number. So what this command here is saying is store the accumulator into the address in IX plus 0, which of course is just the address IX, but that's just the first of these commands. The second one is storing the C register into the address in IX plus 1. And what this does, if I just go over here, is it will take the value in IX, which let's say is C000, just for simplicity, and this load IX plus 1 comma B will take the C000 plus 1, and so that will be C001. This is now the destination, so that memory address will be loaded with the value in the register B. But IX never changes. IX is unchanged by this command. So when we do a command like this, we're not changing IX. IX at the start of these commands and IX at the end of these commands is identical. The offsets are only used as part of the calculation. Well, let's fire this up and let's take a look at what happens. So we've loaded in our test values, hexadecimal 69 and 1234 here, and you can see those test values here, 1234, and you can see that the IX register points to 8340, and you can see that at 8340 we've stored 693412, and that's because we stored the accumulator as IX plus the offset 0, and then we stored C at IX plus offset 1 and B at IX plus offset 2, and that is why these three have occurred. But despite using all of those offsets, IX at the start and IX at the end were exactly the same. So this is different to doing something like this where we're changing HL each time. Now in this case we've used load commands, but we have other options as well. We can increment IY minus 1 and decrement IY minus 2. Well, IY points to 8348, which would be over here, this 0 here, and so minus 1 is pointing to this value here, and so that has been incremented and it's changed from a 0, it's changed to a 1, and then IY minus 2 has been decremented and that's changed to an FF. Now the range is the same as before with our jump relative. This is an 8-bit range, so minus 128 to plus 127. Now, what is this useful for? Well, the main thing that I find this extremely useful for when you're writing games is this is the way that you can pass a pointer to an object, to a subroutine, and that object can contain a set of predefined data. For example, in a game I was writing recently, I had an enemy sprite, and there were lots of enemy sprites, but you would send IX with the pointer to the start of the enemy sprite data, and then IX plus 0 might be the X position, IX plus 1 might be the Y position, IX plus 2 and 3 might be the memory address of the bitmap data, and by doing this your subroutine can read in quickly all of that data from the various offsets, and you've got a subroutine that can easily be worked to point to different objects, and you can make your code also very clear. We can specify symbols like this, and then we can use those symbols in our code. So we could do xpos here, and we could do ypos here, and this would have the exact same function. The assembler would compile it the same, but we've now got a very nice clear piece of code that tells us what the data we're loading in, so that when we look at our code later on we will understand what it's doing. Now, the final important thing to understand about the IX and IY registers at this point is that they're actually 16-bit pairs in their own right, and this is something that was undocumented at the time of the Z80's release. But basically, IX and IY are made up of two 8-bit parts, and these are referred to as IXL and IXH and IYL and IYH. And so we can work with these in separate parts if we wish. And so in this case, we've taken the IXL and we've loaded it with the value 69 and IXH with the value 77, and you can see that happened here. And then what we've done here is we've loaded the accumulator from IYH, and you can see IYH was 83 and the accumulator has been loaded with 83. Now it's quite limited, and there's some rules that might seem a bit odd with the IX and IY registers at first. Some commands can work with them, and some registers can work with them and some can't, and it might seem quite strange. So what I'd suggest you do is again check that cheat sheet for the full breakdown of the commands that are possible and the commands that aren't. One final thing to understand is because there's extra data being specified here, these offsets are an 8-bit value, the commands are physically larger in the compiled code than a command that used HL, for example, so they're going to be bigger in terms of your program size and slower in terms of the running code. So for example, using the IXL and IXH registers in this case is going to be slower than using, say, H and L. But if you've run out of registers, then that might be the best thing you can do. I certainly do it. So definitely not to say you shouldn't do it, shouldn't use those commands. It's to say those commands have a larger cost to your programming speed and memory, so you should make sure that the times you're using them, they are the best option for you. And again, these, as I've said before, these are going to be commands and things that you may not need, understand, or see the purpose of at this stage in learning Z80. They're just something to put in the back of your memory for later on, because you will start to think, I want to do X, Y, I don't understand how to do these things, and then you'll think, hang on a minute, that in indirect addressing using the IX register, maybe that can help me out with this, and that'll probably be when you want to come back to this, and it will start to make more sense to you if it doesn't at this stage. The next one is super simple. Implied addressing. Now this is where the commands themselves need no parameters. The destination or the source of the command is implied in the command itself. So for example, the neg command, this will negate the accumulator, and it only works on the accumulator. So you don't need to specify any destination parameter here, and you can see here we have negated the accumulator. We've got 0.3 in the accumulator here. Well, let's just check that out. So if we go to our calculator here, and if we type in a 3 and then we negate this, you can see that that becomes FD. So FD is -3 in hexadecimal, and you can see we've repeatedly run the neg command here, and that's repeatedly toggled from 03 to FD. So the fact that the accumulator was the destination was implied in the neg command, so we don't need to specify anything else. Another example is the CCF command. Now this stands for complement carry flag. It doesn't stand for clear carry flag. You might see the CCF and think it does. Don't worry if you don't know what the carry flag is yet. I've not covered it. We're covering it later. Again, I'm going through everything in completeness in this lesson. We're going to come back to a lot of this later on. Anyway, here you can see the carry flag in this F section. That's the flags. And each time we've complemented the carry flag, we've effectively flipped the carries. So it's gone from off to on to off to on. And that's what the CCF command does. So implied addressing doesn't always mean the accumulator. In the first neg command it did, but CCF doesn't use the accumulator. So implied just means that the command always works on that register anyway. The last one we're going to look at is another one that's a bit tricky and not something you're probably going to need to worry about in the early days, but this is again quite an interesting one, and this is bit addressing. Now bit addressing is where, rather than working on an entire register or a memory address, we actually work on a single bit of a register. Now of course all of our registers are 8 bits, so if we just load our calculator here with 255, you can see this contains 8 ones here. And that's what this bit addressing does. So this allows us to alter and even test single bits of our registers. So here we're going to load the accumulator with F0 and the B register with 00FF, and then we're going to do some bit level commands on these registers. So here we're going to set bit 0, which is the least most significant bit, the bit on the far right effectively of the accumulator. And this is going to change our F0 to an F1. Now, of course, if we just get our calculator up again and we load in a value of 1 here, well, you can see that 1 is the least most significant bit here. Now, what we've done then is we've set bit 1 of B, which is actually the sort of in order the second bit, if you will. So bit 0 is the first one, the rightmost, and then bit 1 is the second rightmost of B. Now, if we look at our values here and we go over to our binary here and we type in 1, 0, that second bit is effectively worth a value of 2 if we can use the word worth there. So setting bit 0 of the accumulator has changed the F0 to an F1. Setting bit 1 of the B register has changed the B register from a 00 to a 02, because, as I say, the second bit here is a value of 2. Now we can use the set command to set bits. We can also use the reset command to reset them. So here what we've done is we've reset bit 0 of the C register, and this has changed the C register from an FF to an FE. And then what we've done is we've reset bit 7, which is the most significant bit. So if we go to our calculator here, so bit 7 is that bit there. That's the most significant bit of an 8-bit byte. And that has a value of 128 or hexadecimal 80 here. So when we've reset at bit 7 of our accumulator, the F1 has become a 7-1. And then we've reset bit 1 of our B register, and that has gone from the 02 back to a 00. So here we've used the set and the reset command with this bit addressing, where the bit is specified here. But there is also another command, which is the bit command, which is for testing, and we're going to look at that in a later lesson when we do some comparisons and some branches. So we're going to cover that later on. The bits that are specified here are always a fixed number. You can't use a pair of registers here. Again, I'd suggest you go to the cheat sheet and have a look at that to see the possible combinations of this command. Anyway, that's actually all we're going to be covering for today's lesson. Now, as I always say, please go to the website and download the cheat sheet and source code and the build scripts and have a go with all of this yourself, because really the point of all of this is you should be trying this out yourself. I know it's difficult in the early days, you know, it's quite uncomfortable sometimes and you don't know what you're doing, but you need to at least take these and just change some of the fixed values and just see what compiles, see what doesn't, check it works the way you think, and you'll start to understand this more. Now, this is just the second in the series, so we're going to be going into more complex topics later on, and of course once you've learned the basics of Z80 you can look at my platform specific series, which covers the actual stuff on individual hardware systems depending on which system you're interested in. Anyway, I hope you've enjoyed this. If you have, please like and subscribe. If you like videos, YouTube recommends them to more people and it really helps me out. Anyway, thanks for watching today and goodbye.